two classes today, right? So I will start with this general introduction without going into any details. So this will be just very hand-wavy introduction. And after that, during our second hour, we'll have a seminar where we will actually compute something. We will start with computing something simple, namely, for our first seminar, we will discuss Puris numbers, and we will just try our hand in computing them in some very simplest cases. After that, we will go on. So we will not go into the details of the topological recursion itself from the start. We'll start with applications, and once we know some stuff about Puris numbers and some other examples, we'll see how topological recursion works there, and then only after that we'll go into the detail of what this topological recursion is. But right now I will start with a hand-wavy introduction. Okay? So please interrupt me at any point if you have questions. The same goes for our online participants.
So
yes.
At some point, we should say something about the organization of the course itself, but maybe later.
Yeah. We will maybe let's maybe do this at the end of this first hour. After I give the introduction, we will talk about the organization of the course itself. But also, we have a Telegram group. So, Boya, could you please?
Yes. I'll send the link to the chat.
To the chat. So our participants here, you can enter this chat via the link in the. So we have in the timetable on the faculty website. There is a link to this meeting, and then you can in the chat get the link to our Telegram group. Or I can maybe write it down on the Blackboard, but I think it will be easier for me to copy it from the chat. Okay? So, speaking of our online participants, do you hear me well?
Yeah.
Okay, great. All right, so what is this topological recursion? So actually, if you just say topological recursion, it's ambiguous because there are several things in math which are called topological recursion, and what we're going to deal with in this course is what's called spectral curve topological recursion, or Chekhov-Einara-Antan topological recursion. So let me write it down. So we are going to deal with spectral curve topological recursion. Also, which is also called Chekhov-Einara-Antan topological recursion. So it's not to be confused with other things which are also called topological recursion. Actually, I think we will mention at least one of the other topological recursions a bit later in the course, namely the one dealing with homology on the modular space of curves, but about that later. Anyway, so what is this thing? It first appeared in the context of so-called matrix models coming from physics. So these matrix models, they are basically toy models of quantum field theory, where maybe, have anyone of you heard of quantum field theory or matrix models? Okay, so in quantum field theory, you have infinite dimensional spaces, and you have to, in this Feynman approach, you have to integrate over some infinite dimensional spaces, and it's quite complicated. And physicists try to understand what happens there by studying certain toy models, where they replace the infinite dimensional integrals with finite dimensional integrals over spaces of matrices. For instance, over Hermitian matrices. But the structure of the integrals they studied was basically of the form that is found in quantum field theory, and it was useful to physicists to study these finite dimensional toy models in order to understand some stuff which happens in their real problems in the infinite dimensional cases. But I mean, some stuff is similar, some is not. In any case, so it's not very relevant to our discussion, but okay, I will not even write those integrals right now. But matrix models, it developed into a theory, into its own theory, not even in relation to quantum field theory. And you study certain integrals over spaces of matrices, and it turns out that some important objects which appear there, which are called the resolvents, they satisfy some recursive relations. So the resolvents in matrix models, satisfy recursive relations.
By the way, microphone seems to be in this black whiteboard, so we hear you much better when you are close to the whiteboard.
It's better if I speak like that.
Yeah, it's much better than previous, like half a couple of minutes. Yeah.
Yeah, please tell me if again I'm not heard very well.
No, it was okay, but now it's better. Yeah.
Mm-hmm. All right, so I will not write down precisely who are these resolvents and what are the recursive relations on them right now, but this is the origin, and out of this picture coming from physics, basically these guys, Chekhov and Aron, they developed more general. They generalized these recursive relations, which they found studying matrix models. They generalized it into a more general context, not involving matrix models. Why is this? Okay, let me write it down. So, what is this? Concept here, which Chekhov and Aron, which they presented. So basically, you start with, why is it also called a spectral curve topological recursion? So you start with some algebraic curve, or one-dimensional complex manifold. So this is an example, but in most cases, we will actually be dealing with a sphere. So CD1. Let's even for the moment forget about the more general cases of spectral curves. in most applications, the curve is a sphere. So this will be our spectral curve. Spectral curve. So it's a one-dimensional complex manifold. With additional structure. So we'll have some additional structure appearing on this on our curve, and after that we will call it the spectral curve. So a spectral curve is a complex curve with additional structure. So what is this additional structure? There are certain variations. We'll start with the simplest case. So in the simplest case, so let's for the moment think of CP1, just the sphere, and on the sphere, or on the on a more general curve, you have two functions, x and y. We assume that these functions, x and y, are some meromorphic functions. Or in the very simplest case, you can even assume, so you can assume that on CP1 we have some maybe even rational functions. So this will be our curve sigma. Meromorphic functions in sigma. And moreover, we assume that we will look at the critical points of x. So we'll look at this equation dx equals 0. Okay? And we say that x have some. So let's introduce some coordinate on our curve. So in the case of the sphere, it will be just our global coordinates. So let's say that it has some global coordinates then on this Riemann sphere. So dx equals 0. It happens when z is dx of z. Belongs to some set P1 and so on. Pn. So we have some points here. These are the critical points of x. Okay. So P1 and so on. Yeah. The critical points of this function x. And we assume that this x that they are simple, basically, right? So in the sense that near pi, we can produce some local coordinate. Let's say z tilde. Such that x is equal to z tilde squared, right? In the local coordinate, we have simple branching. Okay.
there won't be a point with more complicated.
Sorry?
Won't there be a point with more complicated amplification profile?
We'll not consider this so far. So actually, in our time, in the chat in our time, topological recursion, this is forbidden. So you only should have simple ramification. But there are generalizations. So for instance, there is so-called Bouchard-Renard recursion, which allows more complicated ramifications, but it's not. Actually, there are multiple ways to generalize this. So let's consider just simple ramifications.
Excuse me, can X be a Z tilde square plus 1? For example.
Oh, okay. So let maybe say that it's like that. Okay. Yeah, thank you for your comment. Yeah, this would be better. So okay, so we have these two functions. There are some conditions on y as well. So it shouldn't have poles at these critical points, but let's leave that for when we go into more details. So let me just say what is our recursive procedure. So we start with two objects, which are called omega 01 and omega 02. Who are they? So omega 01 is just y dx. Omega 01 is just y dx. And omega 02, it's what's called the Bergman kernel. So, but let me, at the moment, let's not go into the details. Let's just consider the CP1 case. In the CP1 case, it's quite simple. It's this guy. So this is omega 01 of z, and omega 02, it depends on two variables, z1 and z2, and it's equal to, sorry, it's equal to dz1 dz2 over z1 minus z2 squared. So who are these guys? As you can see, omega 01 is just a one form on our CP1. So this is in the CP1 case.
Maybe some example. What does it mean when y and x some functions on z of z? Yes.
Mm-hmm. Yes, for instance, okay, so I'll just let me for now say what are these objects again. So what is this omega 01? You see that this is just a one form, right? Y dx, it's a one form. And this guy, we say that we have two copies of our sigma here, of our curve. In this case of the sphere. Okay, so it depends on Z1 and Z2. So it's defined on product of two spheres, right? And on each of them, it's one form, but guy like that, you see, right? Is it clear what is this sort of object?
It's a section of certain line bundle on the product.
Yeah, so you just take a product and you can call it as endpoint differential. So you can say that this guy is an endpoint differential on our curve. Okay.
So we take a complex of attention bundles by contraction and
Yes. So you can, for instance, you can write like that, or you can omit it. So
that means that each time you have CP1, this omega 02 will always be this guy.
Yes, in this, each time we have our curve to be CP1, it's always this guy. Nothing else. So just always this guy. In the higher genus, so if you have genus 1 curve, for instance, it's a bit more complicated. So there are some conditions on this. Like I said, at the moment I don't want to go into more details on that. We'll cover it further on. But let's just, for the moment, think of this guy. A little bit later, I will give more examples. And what is this topological recursion about? Is that we want to recursively define objects like that, omega gn, which are labeled by two numbers, g and n. This g is, in some sense, it's related to some genus, but not to the genus of our spectral curve. Okay, so it's g for genus, but not the genus of spectral curve. And we'll see it a bit later. So out of those two guys, we'll construct omega gn for all g and n, and they will be of this sort. So they will be n-point differentials. So this is a bidifferential. So this is a one form. Omega 02 is a bidifferential, and omega gn is an n-point differential. Okay? A little bit later, I will give the precise formula. So we define so these guys, they are defined recursively starting from omega 01 and omega 02, and we also need to use the PIs. And PIs are used. So it's basically the precise formula. It constructs some combination of all the lower omega gns, and then takes a residue at every point pi. So I will write it down a little bit later. It's a bit large formula, but first let's discuss what we have here. So far it looks like some abstract construction, which it's not clear what does it have to do with anything, right? Why is it interesting to, in some artificial way, to construct some n-point differentials on some curve? Why is it even interesting? The point of why is it interesting is that these omega gns, if you supply various starting data, so we have this starting data. Starting data is our spectral curve. So curve equipped with this functions x and y and the Bergman kernel. So from the starting data, let's maybe write this down. Starting data.
I'm sorry.
Let's say initial data.
Didn't you write tensor product between DZ1 and DZ2, or?
Yeah, well, I mean, let's usually omit it, but you can write it like
that. But not tensor. I mean, it's symmetric. So yeah. Okay. Not wedge. Yeah, but yeah.
On two copies, so it's not. It's actually.
Yeah, like.
Initial data. Our initial data is this curve sigma x, y, and you can say that omega 02 can be included in the initial data, but if it's the sphere, then there is no freedom there. But let's maybe also include it. Sometimes it's called, this is also called B for Bergman, B of Z1 and Z2. But there are some conditions on X, Y, and T, like I said, and for the sphere, there is absolutely no freedom for B. And I mean, anyway, so we have this initial data, and from this recursion, so our topological recursion produces omega GNs. It produces this whole tower of omega GNs for all G and M. So where G is greater or equal than 0 and M is greater or equal than 1. This whole tower of omega GNs is produced recursively starting from this initial data.
And if you take any initial data, does it always give something meaningful?
Let me go there. So now, why is this procedure interesting? This procedure is interesting because it turns out that by, you see here, we have only some small number of objects here in the initial data, right? But it turns out that if you supply appropriate initial data, then one and the same recursive procedure, the recursive procedure is the same, you obtain as these omega gens, they turn out to be generating functions or answers to quite many seemingly unrelated problems in various parts of mathematics. So let me maybe just list this a little bit. So why we are interested in that? So this will be, omega gen will be a generating function for some numbers. And these numbers, they end up being answers to some interesting problems. And these problems are even seemingly unrelated. But they are produced by one and the same recursion where you just swap the initial data. Okay, is it clear? So this is the most important point here. There are some variations, but usually what we say is that omega gn, we can expand it as a series. There are slightly different ways to do this, but usually you can write it like that. You can say that this is sum over Young diagrams mu with the size, sorry. Let me write it just like that. So sum over mu1 and so on mu_n. And we can write here h g mu1 and so on mu_n. I'll have to write it again because it overlaps. Sorry. So we take our omega gen and we expand it as a series. So we say that it's sum over mu1 and so on mu_n, h g mu1 and so on mu_n times usually we write it like that. moment. So, as I said, there are slight variations, but in many cases you just take x. So you expand it in the powers of x. So you write x1 to the power mu1 minus 1 dx1, and so on, xn to the power mu(n) minus 1 dx. So basically, what you do is you expand this in the powers of x as a series. And here what you get, h, g, mu1, and so on, mu(n), they are some numbers, the series coefficients. Okay? Yeah? Or, well, sorry, it's a little bit, yeah, let me call it h small. So these guys are just numbers. And these numbers are precisely what I referred to when I said that we obtained some answers to various questions in this math. So let me list some cases which appear here. So for instance, our most basic example, which we will consider, and in fact, we will start with it the next hour, is the case of Fourier numbers. So maybe some of you heard about Fourier numbers. Okay, so the Fourier numbers, they appeared more than, I think, in the 19th century already. So they have two interpretations, a combinatorial interpretation and, let's say, geometric interpretation. I will actually go into a little bit more detail about them, and we will study them in more detail next hour. Basically, let me just say that simple Fourier numbers is a way to is the number of ways to represent a permutation of a given cyclic type in terms of as a product of a specific number of transpositions. Okay, I will write it down a little bit later. There are generalizations of that, so you can find not only what's called simple Fourier numbers, but there are many variations of that. Monotone Fourier numbers, Bychkov numbers, lots of things like that, with for instance, R-spin Fourier numbers, orbital Fourier numbers, and generalize them in many ways. And this is the first example of topological recursion's work, because if you supply to the topological recursion appropriate initial data, you can produce all sorts of Fourier numbers. So for instance, for some specific x and y, you get simple Fourier numbers. If you change it a little bit, you get monotone Fourier numbers. Change it even more, you get R-spin Fourier numbers, and so on. So this produces, as our first example, all sorts of Fourier numbers. Like I said, Fourier numbers will be the first example which we will study in detail. So we will get precise definitions, and we will see how it appears here, this recursive approach. So is it clear what our first example is? Any questions so far?
Does this mu I non-negative?
Yes. So actually,
So is it clear what this sum means? I mean, sum of mu1, etc., mu(n), and who are these dx1? So please ask questions, because, or maybe Petya, you could a bit in a few in more details too. Yeah.
So the sum over this mu i's, it goes basically they are mu1 on mu n. They form because you see here it's this should be in fact symmetric in the end. It should be symmetric under permuting I 1, 2, 3, and so on. And so we can actually think of those guys as being Young diagrams. So yeah, we sum over non-negative mu's. Okay, so what are the? Let me also mention some other examples, which we'll cover further on. So besides Fourier numbers, we get the so-called Gromov-Witten invariants. These are a bit more complicated. They appear in the basically in algebraic geometry, in the theory of when you study the homology of moduli spaces of algebraic curves. We'll discuss them a little bit later on. Also, you get certain knot invariants, for instance. So, for instance, if you have torus knots and consider the colored conflict polynomials of torus knots, they also can be obtained by topological recursion with appropriate initial data. So let's maybe write down our main examples. Fourier numbers.
And also maps, so ribbon graphs, yeah, combinatorial maps.
Yes, maps. Maps counting, maps and generalized maps counting.
So maps, we mean here ribbon graphs or fat graphs, also embedded graphs, the counting of different kinds of embedded graphs.
Counting. Not invariants. Let's see. Does anyone know, is there a way to...
Это вправо, видимо, что вправо страница.
Да, можно ли это видеть снизу? Не знаю.
I see now counting and then...
Yeah, but I just, the page ends and I want to keep writing below that.
Да, две страницы справа внизу.
Да?
Извините, пошла.
Она все равно справа, получается. Так, сейчас. Ну. Вот. Okay. So maps counting, then not invariance. Oops. Not invariance. Well, I mean, not any not invariance, but for instance, harmful polynomials of torus knots. What else? Volumes of moduli spaces of algebraic curves. So basically, these will be our main examples. And like I said, the most important thing is that we have quite a few, and like I said, seemingly unrelated examples where one and the same procedure gives generating functions for the answers to these problems. Okay, so is this message clear? And we will study in detail some of them. So what else I wanted to say is that, okay, this is nice and all. I mean, this is curious that one and the same procedure gives these answers, but can it be used somewhere? I mean, is there some application which produces of this whole theory, which would solve, for instance, some problem which people already wanted to solve before we introduced this theory? And there are examples of that. So, for instance, let me mention this. Applications. So one application is the so-called Zvonkin's conjecture. What is this Zvonkin's conjecture? So basically, it all started with the it generalizes the ELSV formula. So what is this ELSV formula? ELSV formula is it is a formula which relates H G mu, simple Hurst numbers. So it relates them with certain integrals over moduli space of algebraic curves. So I will not at the moment go into the details, but we have here so certain integrals over moduli space of algebraic curves. Yes, over MGN bar. Yes. like I said, so I will not write this formula precisely at the moment, but on the right hand side there are some integrals in the cosmology of the Lin-Mumford interpretation of the moduli space of algebra recursion. On the left hand side we have Hurwitz numbers, and these guys, like Adao, Landau, Shapiro, and Weinstein, they, using some complicated geometric techniques, they proved this formula, this relation. There is actually some specific equality, which I'm not writing in detail right now, but anyway. And Zvonkin conjectured that that a very similar formula holds for generalized case, where on the left you have what's called the R-spin Hurwitz numbers. So Zvonkin's conjecture is where you relates R-spin Hurwitz relates with integrals of Kyoto classes. And there are some even further generalizations, and it was a long-standing conjecture. So actually, Zvonkin, studying this simplest LSV case, Zvonkin came up with this conjecture, but using similar techniques to how the LSV formula was proved, it turned out to be very hard to attack this conjecture. And over, I think it, don't know precisely, but something like over 50. I mean, it's no one knows how to prove it in a similar way as the LSV formula was proved even today. So, and it was formulated like I think in 2006 or something like that. So it was a really long-standing conjecture, and for more than 10 or about 15 years, no one could come up with any idea how to prove it. And it turned out that it can be somewhat easily proved via topological recursion. So topological recursion gave us a tool to gave us the necessary tool to prove this conjecture. So actually, it's not a conjecture anymore. So it proved was proved one topological recursion.
When was it proved?
About 4 or 5 years ago. Yeah, so this is a somewhat important result in this field. I mean, in this field relating purely combinatorial stuff like Hurwitz numbers and the intersection numbers on the moduli space of curves. It was, I mean, somewhat interesting. So, but this is just one application, and it turns out that you can even there are more. I mean, topological recursion uncovers more relations of this sort. So not just the Zvonkin's conjecture, but you can, on the left-hand side, consider various types of Hurwitz numbers or other numbers, and then topological recursion gives you a way how to see that it corresponds to some intersection numbers on the moduli space. So its applicability is quite wide in this setup. Okay, so this is just one application. There are other applications which I will just mention without going into more details. So there is this so-called free probability theory, where they had some open questions which could be answered by topological recursion. And some people even use topological recursion in some seemingly completely unrelated stuff like biology. So people use it to consider the problem of counting some forms of RNA molecules, and it turns out that this topological recursion is applicable there as well, so even biology. Anyway, so these are some specific applications where it helps to achieve something outside of this field, but it also gives you a tool, a purely computation tool. So, for instance, if you prove that for your problem the topological recursion relation holds, then you can use it to compute the numbers. It's not always the most effective way, but you can use it in some applications. All right, so are there questions so far? So is it clear more or less what our course is going to be about? So we will, let me outline it. So we will study specific examples. We will start with Hurwitz numbers and their generalizations. We'll later on mention this theory, this stuff regarding Ron-Witten invariance and the intersection numbers in general. And we'll see how topological recursion works there. And there are also some interesting relations to other areas of mathematics. So, for instance, this is not specifically about topological recursion, but there is also this question of integrability, or more specifically, KP integrability. So, what is this about? Again, I will not go into the details right now, but there is this so-called Kadamtsov-Petriashvili hierarchy, integrable hierarchy, which is an infinite collection of differential equations, and it is very important in many areas of mathematics and mathematical physics. And you can consider solutions to this KP hierarchy, or solutions to this infinite power of partial differential equations. Solutions to KP hierarchy. And it turns out that, for instance, if you look at Hurwitz numbers and you construct the generated functions, which are basically the ones which I wrote above, just if you collect them all together, you get basically a solution to KP hierarchy, tau function, KP hierarchy. And in many cases, when you have topological recursion, when you combine all your ohmic gens together, they, not always, but in many cases, this gives a solution to KP hierarchy. And it's interesting how this, why do we have this integrability property, and what are the transformations which preserve this property. So for instance, natural question is in topological recursion, what happens if you swap x and y? Okay, so you have two functions, x and y. What happens if you just interchange them? This is quite a natural question, right? So it turns out that, for instance, the KP integrability property in that case still holds. So there are some further interesting properties of that. So we will mention this as well. For instance, for Hurwitz numbers, it's not very complicated to see that this holds. And we will see somewhat soon. So this will be also touched upon in our course. But like I said, so what we're going to do is, again, is we will study these sorts of objects. We will see how the topological recursion works there. We will even compute omega gens by hand for some examples and see how the formula itself works. And like one of the goals, by the end, probably we'll be able to discuss stuff like that as well. So we will cover some material on the right-hand side, which is a bit more complicated, but at least we will, in some form, discuss it. Okay, so I think at this point, maybe let's discuss the organization of the course. What do you think?
Yes, okay. So in fact, you have time, so you could, yeah.
We have like 10 minutes. So,
15, yeah.
Other questions regarding this outline?
A very general question.
Yes.
Suppose you have a family of numbers that depends on genes and partitions.
Yes.
Is it always possible to find a topological recursion for them? Like a general question.
Yeah, this is a very natural question, and you can. I mean,
Maybe could you repeat question for their?
The question was: suppose you have some collection of numbers which depend. Suppose I have some numbers a, g mu. So g mu 1 and so on. So suppose I have some collection of numbers which depend on this number g and on the integer partition mu. So we have some collection of numbers. So the question was how to figure out whether these numbers satisfy the topological recursion. So this is a very natural question, of course, and well, it's not always straightforward, but so first, what you can start with? You can start with just by studying the initial numbers, just the one, for instance, 1 point and the 2 point function. And you can start with figuring out what, well, the simplest relation is how this omega 0, 3, the first of the omegas, which is not given in the initial data set, how this omega 0, 3, what is the formula for omega 0, 3. And you can start with checking whether for your numbers this agrees with the topological recursion form. If it agrees, then you need to have some sort of a relation on those numbers. So, for instance, for Hurwitz numbers, you have the Kaplan-Joint equation. This is right. Simple Hurwitz numbers, you can start with the Kaplan-Joint equation. You can prove topological recursion. So you need to have some sort of a relation there, which you can try to convert into the topological recursion form. But it's not always simple. So, for instance, for simple Hurwitz numbers, the Kaplan-Joint equation is somewhat easy to go from it to topological recursion, but already for generalized Hurwitz numbers, it's more complicated. So for our spin Hurwitz numbers, it proved to be very tricky to proceed from Cartesian equation to the topological recursion. Whole huge formulas, many pages, and in the end it turned out that so for instance, it turned out that it was much easier to like to prove topological recursion if you know something about the generating function for these numbers. So for instance, for Hurwitz numbers, in most cases, even for generalized Hurwitz numbers, you know this KP integrability property, which is somewhat easy to see there for Hurwitz numbers. And starting from there, from this KP picture, it turned out to be much easier to prove topological recursion than just by using the Cartesian equation. But again, there is no single answer as to how to figure out whether your set of numbers satisfies topological recursion. In somewhat general, so for instance, as of now, we have a quite general setup of generalized in very general way. We can generalize Hurwitz numbers where we can see that the topological recursion holds using this KP stuff. We will discuss it later. But you will have your collection of numbers coming from something completely different, then you can't say right away. But you need to use something you know about. But we'll see how, like I said, for very general examples related to Hurwitz numbers, we will see how to see that the topological recursion holds. This will partially answer your question. I don't have to go into the details right now. Any further questions? All right, so let's discuss the organization of our course. So we will, like every week, we will have one lecture, one seminar. On the seminars, we will just review stuff, and we will have